Okay, welcome back, everyone. We're going to start our next talk. Okay, we have our next speaker, which is our keynote speaker, Dr. Polo Chau. He's an associate professor in the School of Computation Science and Engineering in the College of Computing at Georgia Tech, co-directs Georgia Tech's MS Analytics Program, Director of Industry Relations of the Institute for Data Engineering and Science, and the Associate Director of Corporate Relations of the Center for Machine Learning. His PhD is in Machine Learning from Carnegie Mellon University and won CMU's Computer Science Dissertation Award, honorable mention, as well as grants and awards from organizations such as NSF, DARPA, Intel, Microsoft, and NVIDIA, and also has had his work covered by publications such as Wall Street Journal, Fortune, MSNBC, and Online and Gadget. Let's welcome Dr. Polo Chau. Thank you.
Thank you. Thank you, thank you. Thank you very much for the invitation, and glad to be here today. So today I'm going to talk about human-centered AI, very timely, I think, particularly in the current wave of generative AI and all the executive order I'm sure you all have seen. Particularly focusing on the work that we've been working on lately on safe, interpretable, and trustworthy analytics. And I'd like to first thank my students. So I named my team the Polo Club of Data Science, so I have fun with the name. And we work at the intersection of AI and human intelligence, so AI and HI, particularly on developing safe, interpretable, and trustworthy tools to help people make sense of large amount of data and complex models. And my current PhD student, master's student, and undergraduate student on the top, and a recent alum at the bottom. So everything that you see today, they're done by them. Yes. And the major research threats, as we mentioned, safe, interpretable, and trustworthy. So why do we focus on those, right? So safe AI, I think this is probably pretty easy for you to get connect with, because every now and then, unfortunately, we'll see these kind of accidents. One of the most prominent, you may remember, is an Uber accident where a pedestrian in Arizona was killed. It was at night, the car was driving towards the person was pushing a bike, and it was too late. By the time you really recognize, oh, it's the person, already hit that person. So AI now is used increasingly in safety critical applications, so very, very important to study both the threats and countermeasures. And you may say, well, that's mostly for safety critical thing, but not really anymore. So it used to be a joke. Actually, there's a comic that says, oh, you have this toaster that is working really weird, right? So you have a chip in it. But, well, actually now smart toaster, actually smart anything you can imagine now exists. Even light bulb has a chip in it. So it's no longer something that only for safety critical application need to worry about. And also only these kind of security risks would increase even more over time. So there's some a little bit outdated numbers. The high level bit is going to be even more serious. And if you ever ask someone working on security, particularly security AI, you ask them, hey, so you're working on security AI, so you have really great protection, right? So for, protecting all the citizens from harm. If you ask them, how does it work? Well, the little secret is they don't really know. Because often AI, particularly nowadays, very complex. So often used as black boxes. I'm sure you have heard of this a lot of times, right? So that means like, how do we really help people understand what's opening? So that is working. So that's where our interpretable AI first come in. So we want to make the black box a little bit more translucent. So keep in mind that we're not trying to explain every nitty-gritty details because it's too complex, too many numbers. But rather we want to make it a little bit more relevant to the user's task. And then a way of doing it is through interactive, scalable visual tools to help people understand this complex machine learning model. But just understanding that is not enough because after all, so if you're talking about deploying these tools in real world, people need to know how to use them. So very usable tools and also how to trust them because people do not trust them or it doesn't matter how powerful they are. So that is where our trustworthy AI thrust come in, providing usable tool for the end user. End users here could be domain user, could be expert people who really get touched by these usage. So that's the main agenda for today. So I try to connect all these pieces, safe, interpretable AI, trustworthy AI. So they're very, very tightly connected. So particularly for today, I'd like to give you an overview of our work in all these three thrusts. I'll start with the Save AI thrust, where I talk about some of our latest work in both attack and defense for AI. So attacking as in how do we study the vulnerability of these models, where I will talk about an example called Shapeshifter. It's ongoing work funded by DARPA under the DARPA Guard program, and also some of very, very recent work on LLM self-defense. LLM, I'm sure you all have used it by now, but they are vulnerable. So you can manipulate them, you can nudge it to say whatever thing you want. So how do we protect these LLM from harm, misuse? And then after that, I will move on to the Interpretable AI thrust, where we show some examples of how we can help people understand what these complex models are doing. So for that, we'll talk about examples like Summit neurocartography and some of the most recent work called Risk Maps, to how to help people visualize what these models have learned all in browser. You don't need to have like a powerful GPU supercomputer, and they can all do all those in your computer. And lastly, wrap up with our Trustworthy AI thrust. How do we provide these tools to help people understand what is happening and how do we correct them potentially? So audit what the model is doing and also correct mistakes. So I'll start with the first thrust, Save AI, the shapeshifter approach. So it's joint work with Intel. So at a high level, we're trying to study the vulnerability of complex vision model, computer vision model, particularly what we call object detection. And this is a mouthful, I know, so Shapeshifter is the first targeted physical adversarial attack for object detector. So what is that? So you might be very familiar with image classification. So if you're given an image, in this case, that seems, oh, there's a car. You say, oh, this is a car. So classify this as a car image. However, classification is actually not very, very common or as common as another task we call object detection. Because very often, particularly, you have like self-driving car. So your camera in your car is pointed towards a road. They're not only one thing. You are not going to classify, hey, this is a video or image of a car. More often than not, you have many things in it. So that is what we want to do, object detection. So detect the potential objects in that. More complex tasks, because we need to, we call localizing, so detecting what are the potential region of the image that would contain something, and then what those something are. So in this case, that could be people, could be car, could be bus, could be trucks, and so on. So object detection is what we're interested in. So I think by now, you probably have seen a lot, but way too many examples that showing that these deep neural network or deep learning methods are very vulnerable. So what that means is that you can fool them very easily. So for example, if you have an image of a stop sign, so here to you, human eyes, we say, oh, it's probably a stop sign. But it actually can be easily, you change the pixel a little bit, and then the state-of-the-art models will say, oh, this is a max speed 100. Actually, you can change it to whatever you want. So you can do small perturbation, and then you can fool these models. However, good news is, a lot of times when academics are studying these kind of perturbation, we call it manipulation, they have some we call impractical threat model. A threat model meaning when we study this problem, we assume what the bad guys know. So often academics, what we assume is that the bad guys would be able to have complete access to the whole system. So again, using self-driving car as an example. So let's say you want to fool the object detector, like of your self-driving car, which point the camera towards a road. And often we will assume the person who would want to fool this object detector would have access to not only the camera, but also the whole car system. So that means the whole pipeline. Right? So, and what then they would launch is we call digital attack. So somehow they can fool the deep neural network component of the whole pipeline. So this is what was happening a lot in research and academia. And if you really have full access to it, well, you can really do whatever you want. As what I just said, you can change the image of the stop sign into a max speed limit sign. However, we call that this is perhaps a little bit impractical, as in if a bad guy really have full access to the whole pipeline, then why don't you just crash the car? So why do you bother manipulating all these things, spending all the GPU power to manipulate us, right? So that's what we consider as not really practical. However, we think a really serious threat is what we call a physical attack. So as in, the bad guys, even though may not have full access to the whole pipeline, but they could probably manipulate the physical environment, right? So as in, if you want to misdetect a stop sign, you could do something to the stop sign. Maybe either directly on the stop sign or maybe something surrounding the stop sign. And this manipulating physical environment, we said, is more realistic. And you can also, we found that you can actually also do that, right? So I'll first start by showing you some demo of how the attack, shapeshifter attack work, which we developed with Intel, and then I'll talk a little bit about detail how it works. So as I'm going to show a video, there's two stop signs. One's the real one on your left, and the fake stop sign generated by shapeshifter on the right-hand side. So there's a video taken by a student, so he's driving on the top of a parking lot. As it gets closer and closer, you see the real one correctly detected, the fake one originally not detected, and then now detected a lot of people. Pretty scary. So when we first look at it, oh, okay, not good. So we know how to do it now, pretty scary, but there were a lot of challenges that we had to resolve. So for one is that object detectors are actually quite hard to attack initially. The reason is that these object detector, like say the phosphorus CNN method, it actually, you can think of it as like an ensemble model where internally it actually tries to detect within an image what are the potential regions that may contain something. And those bounding boxes that may contain things that actually will overlap. So what that means is if you want to fool this object detector, you need to fool all the boxes. So in a way, you're trying to attack an ensemble. Another challenge is that since we're dealing with physical environment, so we need to be careful about the distance. As you drive further, closer and closer, you want to be this fake stop sign to still be able to fool the detector, and also different angle, different lighting, and so on. So for those reasons, it's not as straightforward as we thought. So however, we thought a lot, my students, I should say, thought a lot about it, and we came up with a solution. So well, since you want to fool ensemble, well, we just attack the ensemble, specifically attack the sum of classification laws. And also we take advantage of the fact that for some of the darker red area, you can actually do a lot more perturbation or changes and still not really susceptible to humans detection. So that's solution one. Another one is where they have a technique called expectation over transformation, very fancy name. So what that really means is once you have some pattern that is generated, so you just paste it on top of different images, rotate it, shear it, transform it, and still want to make sure that that pattern still work across these different backgrounds. If it does, then very likely it's going to work in the physical environment. So together, then we're able to come up with this different pattern. So previously I showed you that you can change the stop sign into people, but you can actually change it into anything. So in this case, I'm showing you a video where it disappeared. So it's not detected at all. And then maybe a few frames, it gets detected as a bird. So get really close. Okay, there's some bird. Right? So pretty scary. It was some time ago. And I also got the attention of DARPA as well. So there's an ongoing program right now, DARPA Guard, guaranteeing AI robustness against deception. So the whole program is dedicated for building defenses, like protection for this AI model. And it highlights the shapeshifter as a state-of-the-art physical attack that we want to protect from. And you may ask, why do we study these kind of attacks? Like if the ultimate goal is to study defense, then protection, why do we do an attack? And the reason is that if we do not know very well what the vulnerabilities are, then our defenses are not going to be strong. So that is the whole motivation for studying the defense. And through studying defense, then we come up with a lot of very exciting results. So this is really is going to be presented at BMVC in a few weeks. Through studying the defenses, we found that existing work, for example, often people actually have different kind of conflicting idea about what would make a, let's say, classification model like convolutional neural network object detection very robust against manipulation. So in our work called robust principle, we discovered that there are generalizable principles that if all these different architecture try to implement those principles, then you can be pretty robust against these kind of attacks. So specifically, not going into detail, but at a high level, different configurations. So our model can have many layers, many stages. So there are actually some optimal, we call depth to width ratio. So the how wide, how narrow, how deep they are. And there are certain optimal range that will make it more robust. And similarly, so a lot of these models, particular, something we call stem stage. So I mean, as an input, would you use something called convolutional stem? So as in, would you scan over an input image with overlapping window or not overlapping window? And then we found that with overlapping window actually also make it more robust. And thirdly, you also find that for some of the blocks, if you use certain smooth function, activation function, also make it more robust. So the significance of it is that means they actually, well, even though a lot of it is empirical, but there are also generalized principles that can work across these models. So that's one very significant discovery that we have by studying these kind of attacks. And also very recently, we study, like everyone else, like to also look at LLM or this generative AI model. Again, by studying the attack, the vulnerability, we come up with, I would say, very easy to use and practical defense we call LLM self-defense. You probably have seen already on the news. So for ChatGPT or Llama or BART, this model, you can coerce it, like with some prompt engineering, we call it, to make it spit out whatever you want. Particularly, it could be some harmful content. So there's a lot of work on trying to make sure these models do not spit out the harmful content, but still, with a lot of ingenuity from a student researcher particularly, you can do that. So here on the right-hand side, you will see some we call adversarial prompt. You can pass in certain sequence of words, and then the tricked LLM will spit out harmful content. So certainly that's attack. So a lot of people say, well, okay, so how do we defend this? Different idea. But what we found is that we actually can go with a really simple approach. So as in, I would let you trick the LLM. That's fine. Trick all you want. So, but what we do is that we will put the LLM's output, even though it's tricked, we pass it back to an LLM. It could be the original LLM. It could be another LLM. Doesn't matter. And we ask that second LLM, is it harmful? So very simple. Actually, you can do it right now. So you don't need any programming even. Just copy and paste the text and then ask is it harmful? And you'll be surprised, it actually worked really well. So the LLM second pass will say it is harmful. So that means it's a very simple, generalizable, effective approach. We can drive this attack success rate all the way down to virtually zero. Very, very effective. And that's also through studying a lot of these attacks to come up with it. And in case you're wondering, does it work for the latest model? Yes, it works. It works for Llama 2 open source model from Meta and also from GPT 3.5 ChatGPT as well. So very exciting work in this sort of safe AI. So that's a quick example of in attack and defense. And as we mentioned, so if you ask people how these attack and defense work, often people say, not really, we're not really sure. So therefore, I need some tools to interpret how these method works. So that brings us to our second thrust of our research, interpretable AI. So particularly, we're interested in using visualization. We think it's a very powerful medium to help people understand how this model works. So we start with some of the original model on a classification model where we're going to help people understand what these model deep neural networks learn. So traditional people want to say, well, deep neural network is too complex, I forget it. To try not to do any interpretation, just use it as black box. But I think, well, not really, right? Because often the claim for these deep neural network is that it's inspired a human brain, although it's not the case really. But they say, well, at least it's inspired a human brain. Something must be learned, have been learned. And so how do we discover what is learned? So particularly, often people would say that for convolutional neural, they'll say, if it has an images, like a stack of images of a white wolf. And then the deep neural network should have learned, let's say, some legs features, some fur features, maybe pointy ears, and then together, then they give you the final classification of white wolf. But that's what people say, and they would claim. But is that really the case? Right? So that's what we aim to find out. So that means at the high level, we want to develop a tool we call Summit that scalably summarize and interactively visualize what these neural networks have learned across millions of images. So I'll show you a quick demo of how Summit works. So there's an interface of Summit. When you first enter the screen, so on the right-hand side, this is the kind of network kind of summary we just showed on the previous screen. So here in this demo, I will use the ImageNet data set. ImageNet is a very popular, over 1 million images data set for benchmarking classification models. And here I picked a class called Tenge. So Tenge is a yellow fish. So that means on the right-hand side, if the model is really doing well, you should see it's learning features like that's about fish, Tenge, right? So here we are picking only the most relevant, most impactful neurons in the model. But maybe to your surprise, we'll find that, well, you say it's Tenge fish class, but you don't see fish, or at least not yet. You see human. You see some eyes, some faces. You mouse over another one, also more human. Even more human, some faces, maybe high level, not only eyes. And as you go further and further up, so further and further up is closer to the prediction, lower, that means closer to the input. As you go further up, then you start to see some fish features. So in this case, some features like getting held in hands. Still good, so some fish, but still some people, right? So the question here for the audience is, well, since we are doing tench classification, and this model is really good, 92.1 accuracy in classifying tench fish. So the question to you all is, why is that? So if it's doing so well, why are we seeing so few tench or fish features, but so many human features? Any wild guess? Yes? You must like fishing, so yes. So it turned out in the ImageNet data set, so benchmark data set that's used in all these research evaluation, it turned out majority of the images are people holding tench, because tench is big. So people like to catch it and then hold it, right? So among all of these, most of them are like that. So that really begs the question, so should I really use this model? Maybe yes, maybe no. If the images that you are going to use or to be fed into the model, like for your application or use case, indeed have people in it, like maybe yes. But on the other hand, if your task only deal with images of fish where there's only the fish, then you may want to take another look. Right? So that was the main discovery. And if you're interested in the details, so we build this graph or this network. We call this the attribution graph. So we'll go very high level how it works, so in case you're curious. So high level is we want to discover these impactful features, representative features, and also the connection among them. Right? So we call the attribution graph. And actually, under the hood, it's not that complex. So there are a lot of neurons, a lot of these nodes you can think of as features in the network. So we try to find out the most relevant ones. So what that means is we pass an image, like actually millions of images, so we pass them all into a network, like from left to right, and then we try to see which of these neurons get activated. Activated, that means like what is the higher value, like when you pass these images through it. And then we take the maximum, like rank them. So get the one that is most excited, like that is, and then we rank them. And then we take only some of them. So because we need to do summarization, way too many, so something need to go. So we'll take only the maximum. And then we do that for all the layers in the model. That's how we get the node, the high-level impactful node. And then we do the same thing for the edges, the connection between the models. So that means for a particular node, we look at the layer before, and then we look at the connections among them. And then we do the same thing. We get like which is the highest, the weight is the highest, and then we rank them, and then we take the max. So by doing that, then you are able to get the most impactful edges as well, and then you do that for the whole network, and then in the end, you'll get the whole graph. So that was a high-level way of how do we get the network that you saw in the demo. Through doing developing Summit, we also found something interesting. I mean, now in hindsight, perhaps not, is there's actually a lot of redundancy in these deep neural networks. So that means that actually multiple neurons or multiple features is pretty much about the same thing. So here we're showing a visualization where we have 3 dot images, one for each row. And then the vertical, the columns here, we call it neurons. So neurons, think of it as a unit in the network. Each neuron supposedly to be detecting something interesting, useful. In this case, these 2 neurons, 460 and 483, they actually detect something very similar. Both of them, particular, you can do a quick comparison. They are both detecting dog faces. So what that means is that 460 and 483, they're actually duplicates. Right? So actually, this is not a well-known part where there's a lot of duplication. And the question is that can we summarize them? Because if they are equally important, you don't want to show them again because then take up a lot of visual space and also like impede human understanding. So how do we group them? So that's the main motivation. And we have an approach, and there's an extension of the Summit tool that we just do. Show you. And specifically, we use a technique called locality-sensitive hashing to all this grouping in linear time, linear in the number of neurons. So a quick screenshot for our neurocartography idea that extend the Summit idea, where on the right-hand side, you'll see, still have a graph-like summary, but now when you hover over one node, you'll see actually multiple neurons. So each row, there's 1 neuron, and particularly the representative images that are activating those neurons. And of course, you may say, well, so you have all these visualization tools. So do people really know how to use them? Do all these kind of grouping, interpretation work really matter to people? Does it align with a human's understanding? So we run a large-scale human evaluation with about 250 mechanical Turk users. And we ask them to rate. So basically, we ask them, say, hey, so there is some neuron groups that our approach, neurocartography, has found. Are they coherent? So specifically, on the bottom right there, we present them 5 neurons, each neuron represented by 9 example image patches. And then we insert another one we call an intruder neuron. So that means a random neuron. So that means they're given 6, 5 is actually a coherent group, 1 is not. And then we ask the participant to say which one to pick, which neurons should form one group. And if they correctly identify those 5, that means its true positive rate is 100%. So there are different combinations. Of course, they may miss one that should be in a group, but they did not pick. Or maybe they incorrectly pick one that should not be in a group, but in a group. So for that, by doing this, then we can able to get true positive, true negative, false negative, and true positive, which also means we can have an ROC curve, which you show on the left-hand side. So we compare neurocartography, our approach, in pink versus handpicked. So that means manual. Manual would be perfect, close to perfect. So here you'll see the area under the curve, 0.97 is perfect, and our approach is pretty close, 0.91. And definitely way better than random choice, like doing whatever. So at a high level, that means it works. So this grouping are meaningful and really group coherent neurons and reduce redundancy. And of course, so far you've seen Summit neurocartography mainly for looking at when we have things that are working well. So natural question is that what if your models is under attack, right? So as in what we saw in Safe AI. So we also use a similar approach. We extend Summit further to develop a similar approach called Bluff. In this case, not for visualizing what's happening when the model is working well, but when it's being attacked. So particularly, I'm showing you a screenshot when the models is being misled to classify giant panda images as armadillo images. So at a high level, that means we want to know which neurons get manipulated. So as you change the pixel value of a giant panda images, which neurons internally get manipulated or activated. For example, here on the right-hand side, zoom-in view, we'll see, so those pixels manipulation cause some scale feature to appear, some bumps to appear, some mesh to appear, and also because armadillo is a grayish body versus giant panda is black and white, so some of the neurons responsible for detecting like grayish color also get manifested. And that's how we get like an attack path in the model to manifest the attack. So something you might have noticed when we show the demo, so we show the graph, like network connection among neurons and other connection. A very natural thing people also want to do is not only show the graph view, but also show what we call the embedding view. So that means, imagine you have each dot here is one neuron. You want all the neurons to be shown at once, like of the whole model at once, and then you do dimensionality reduction, for example, into we call this embedding space. Very, very common, definitely machine learning, as you saw in Summit neurocartography and so on. And also in many fields too, like in chemistry, similar needs. So once you have a different structure, you may want to project all down so that you know which one might be more similar than not. Or maybe in social science also, right? So a lot of different analysis. In the end, you do want to visualize them to help human understanding. However, creating these kind of embedding, particularly visualizing them on your own computer is not really straightforward, particularly when you have millions, tens of millions of points. And also doing it interactively, also very hard. So that means if you say, I want to zoom in, like, can you do that? Well, not that easy. So that's motivated us to build a tool called VisMap. It's completely in browser, and it can handle millions of points. You do not need to install anything. GPU, you don't need powerful GPUs. You can just do all of that in your browser. I will show you a quick demo of VisMap. How do you do the scalable visualization and embedding using a particular data set with a diffusion DB that our group also developed. So diffusion DB is a data set for stable diffusion. So stable diffusion, some of you may have used it in one of these generative AI models where you can type in a prompt, like a text prompt, and say, I want a cat happily eating, I don't know, sandwich, right, on a picnic. And then it will generate that kind of image. So there's a stable diffusion model that can do it. So we collected 1.8 million prompts and also the corresponding 1.8 generated images. And in the model, they also have these embedding, like the dimension reduction embedding that you saw, particular embedding for the part of the clip component in it. So we'll show you how that looks like. So this is a VisMap UI. So because we're dealing with diffusion DB or stable diffusion, so that means we have both the text prompt and the images. So we use blue to represent the text prompt, and then the image in pink. So which is why you see red and blue here. So each dot is one text image pair. So this is at the zoomed out view, but this because they're 1.8 million point, by the way. So on a 1.8 million point, complete in browser, and you can go zoom in. You can show in like a contour summary view. You can hover over any of them. Look at them all if you want, and then look at the text prompt and the generated images. So explore like what are the similar things, what are not so similar. A lot of those. And also if say, oh, I want to find specific prompt and the image pair, you can do that. So let's say I want to find cat. So you can type in cat, and then all the cat images and prompts will get highlighted. So everything also in the complete in browser. And we also have more details there. We have a multi-resolution prompt summarization, so which is why here you'll see we have some of the rectangles, whereas depending on where, how much you zoom in, we show some of the representative text prompt at different resolution. Right? So this is we're really excited about it because this is something that it used to be something you need a server to run, a lot of computation power, but now you can run it, anyone can run it on their own computer in browser, do not need to install anything. So these are demos that you can try right now. So those are some examples of interpretable AI threats that we have. But as we mentioned, just having the tools is often not sufficient. Often you also want the part about the education, helping people understand what's happening. Also, if something's happening or going wrong in the model, how do we fix them? So the rest to our last threats, trustworthy AI threats. We'll show you some example, latest work, particularly in this area. So when we're working with a lot of domain experts, in particular building application who uses AI, we found that not only novice needs help, actually a lot of times the experts also need help. So one of our very early work is working with Google, and let me close this one. With Google, where we want to help the machine learning experts at Google to understand so that they can better train GAN. So GAN is one of the deep generative models, and that was considered one of the most exciting ideas in the past 10 years in ML. So you might have seen these realistic looking images, so also the technique behind deepfake, by the way. So generative realistic images of people that looks real, but they're actually not real. So nowadays, you probably have seen more about diffusion-based method. So for GAN, you can think of it as a previous generation, still a lot working on it. GAN is very fast for inference. If you ever use diffusion-based method, they also can generate these, but much slower. Of course, a lot of people are working on how to speed it up, but GAN is one of the earliest one. So at Google, so they were working on these. And it turned out these methods are not really easy to train. So actually even diffusion also not. But for GAN, not that easy. And particularly it's because GAN internally uses two competing neural networks to generate things that look real, but actually not. So a good analogy is like in the real world, you have these counterfeiter, like the bad guys. So counterfeiter will make fake bills. And then you have the good guys, and then maybe the police. We try to spot the fake bills and catch the bad guy. So internally in the GAN, we call these counterfeiter the generator. So generating the fake but realistic looking thing. And then internally we also have something called the discriminator, who try to spot the fake, so the police. So think of these as two competing neural networks. And what happens is that the generator or the counterfeiter So initially, they're not very good. So they want to generate fake bill, but initially the bill doesn't look very good. So the police have a very good job, easy job of spotting it. But of course, the generator or the counterfeiter would catch up. And the reason the police would do a pretty good job is because the police have access to the real thing, right? The real bill. So then compare, okay, it doesn't look like it, right? So, but the counterfeiter would become better over time. So the second try, the fake bill look better. Right? And then that means the job of the police get harder. And then you can keep doing it. So the police will improve, the counterfeiter improve. And at some point, the counterfeit is so good that the police cannot catch the fake bill anymore. So at that time, that means the training of your gang model is done. So that means now you're able to generate things that look so real that the discriminator or the police cannot catch it anymore. So that's at the high level how gang works. So what I just explained to you that, okay, that makes a lot of sense, but how does it relate to gang? Well, it turned out that this is high level what's happening in gang, but that's just not how people get to visualize or to understand what's happening in gang. So that motivated us, well, if that works well, this analogy works well, why don't we just build a tool called Gang Lab that exactly visualize what's happening, exactly like this. We have two neural network. We will have one big box for each of them, and then we show the flow, like the flow between the two things. So particularly here, I'm showing you an accelerated animation where you see on the left-hand side, the biggest model there, that is the generator, the fake bill, the counterfeiter. And you will see that this is a grid that is morphing. So purple is the fake data that is getting revised and morphed over time. And then the green one is the green dot is the real data. So that means here it is the fake purple data that get revised over time so that it could increasingly look like the real one. So Gang Lab is a tool to help the experts. Actually, now we know, not only for experts, also a novice to understand over time through training, how would these fake data get updated and make it look real. So this is also a tool that you can try in your browser. Don't need to install anything. No need to have powerful GPUs. And when we first released it with Google, so it's really exciting and immediately went viral because there was not really that many tools out there where people can really play with the network directly on the machine. Because often when you talk about AI, like these days, often they say, well, you need to have some GPU power before you can even learn about it. Or maybe if you're in a college, but you need to take these classes, linear algebra, well, when you get more senior, then you learn about machine learning. So we want to change that. We're going to say, why don't we make something that's really accessible, that anyone can go there, that you do not need any special hardware. So that was one of our first tool that we developed. But then we also find that that's actually a very good approach that we can use not only for gang. We can generalize it to other methods too. So for example, we can use it for CNN. So CNN is one of the classic fundamental convolutional neural network. I think you will take a deep learning class. That's probably the very first one we will learn about. And so interestingly, we use this approach. The main motivation for doing it is because I, as an advisor, so my student, they got really excited, like everyone, about AI. They said, oh, we want our group to do more deep learning, like visualize deep learning. And that was about 2015. So 2015, if you remember, that's where deep learning already pretty hot. So in our group, like, well, everyone is already working on it. The bandwagon is pretty full. Do we want to do more of it? And okay, we'll still try, but maybe we have a visualization angle. But once we do that, then I would need to know more about it as an advisor. And then to me, I found that, well, why are these deep neural network, all these are so fancy? Like, what is happening? And I need to read up, including CNN, what it is. And before we have this tool, CNN Explainer, which now you can also go play it in your browser, my impression is that they are pretty complex. So as in a lot of components, a lot of math going on. But once I learned more about it, and I was really excited. So I found that I actually know all these things, the math, the component, and all these things from my undergrad education. My undergrad was in information engineering, so I learned about convolution from signal processing. I learned linear algebra. But then the way that machine learning or AI people, how they develop is they like to make things look really hard. They like to make things look really fancy, so make it very complicated. But then reality is not. So that means to me at that time, I said, well, actually there's a gap, a big gap in education, where we are making things that are a lot more complex than they really are. So which is why CNN Explainer is kind of like a selfish reason of building it. But then we found that it's not only me. It turned out a lot of people also have that need. So we use the same approach as in GANLab, develop it fully in browser. Now the user can go there to the web browser, through the web browser, and then they can inspect all the way from the image input to the CNN. They can hover over all the components. Like for example, here we hover over one neurons in a layer, look at the convolution, the math, connecting the math, and then visualize it. And then you can zoom in, zoom out, go into different level of details, kind of demystifying in some sense. It turned out that all these operations are not really complicated. It's just how existing approaches, how it's used, we thought it may not be ideal. So now this is a tool that's used in a lot of deep learning class, including Carnegie Mellon, at Georgia Tech, and many more. So also encourage you to try it out. And we continue with this approach where now I've been talking about generative AI. So we also have a new latest tool called Diffusion Explainer, also very viral. We just released to Stable Diffusion. So if you say, I type in a text prompt and then I want to generate the corresponding images. So again, like when Stable Diffusion or these models first came out, people considered it as magic. Like, oh, okay, wow, how does that work? Right? So we want to help people learn really what is happening. And we think these tools can be very impactful because by knowing what's really happening, then you can answer questions like, oh, if an image that generates some potential offensive content or maybe some copyrighted content, where does that content come from? Right, so it can help us trace it all the way back to the source, and also knowing the intermediate process, how does it work. So also encourage you to try this out. So far, we showed you some of the example where we do build those tools, like for in-browser tools. And we found that from experience, it takes a lot of work. And you really want to have the motivation and to do it. But we want this to be easier. Like we want to build this animation, these education tools, we want it to be easier. How do we make it easier? So there's one of our latest work by Alec, and he just won the best poster at IEEE Viz, the top visualization conference, where he had this approach, which is to use these syntax of code, and that's very familiar to machine learning experts, particularly PyTorch. So PyTorch is one of the most popular deep learning libraries that anyone now do deep learning they probably would use. So in particular, oops, let me play this. In particular, they allowed the machine learning experts to specify, in this case, a deep neural network, using the same syntax that they would use when coming up with the deep neural network. But then what you would end up getting is the animation or the explanation of how the model works. So that means at a high level, we wanted to make it very easy for the ML experts to create these kind of educational, explanatory animation and not forcing to have to learn new things. Right? So that is something we think is really powerful and is really bringing these visualization interaction to the machine learning expert, make it easy for them to use to generate, and then by doing so, then we help everyone to learn more about these methods. One of the last thing I want to show today is that also our latest work where we say, well, so far, majority of the work I show you is for cases where the models seem to be mostly working well, or you want to explain to people what's happening. But in practice, often when you apply these particular end domains, like healthcare, for example, doctors are really care, like, well, okay, does it really work well? Why does it work well? If it doesn't work well, can we fix it? Like, can we fix it to the right thing? So there's a collaboration with Microsoft. We developed something called GAM Changer. So GAM is Generative Additive Model. You can think of it as a generalization of linear regression. And particularly, I'll show you an example of what GAM Changer can do. So it allows the domain expert, in this case, could be healthcare professional, to inspect what the machine learning model, GAM, has learned, and how each feature of the model is contributing to the final outcome. So particularly here, I'm showing you a scenario or use case for pneumonia risk. So vertical axis here is pneumonia risk, higher risk towards the top. And then on horizontal axis is age. So that means there's a feature, age, that would contribute to the risk. Well, intuitively, as we get older, probably higher risk. So that means what you expect to see is that as we go higher age, like more to your right-hand side, the risk score would go up, which is true for most of it, right? Initially, younger, lower risk, which is good. As you get older, increase. But at some stage, once you're above 100 years old, wow, you're good. Not that risky, right? So why is that? That certainly doesn't make sense. But actually, there's rules that regulate that. Well, for machine learning model, it needs to have a monotonicity. So that means that things should not like go up and down. So if they go up, they should continue to go up. So Game Changer allowed the user, what you just saw, is to interactively modify the machine learning behavior so that it would meet the expectation. So human expectation, different ways that you can do it. And also when you are doing it, you can see how you are doing the model. So here it's being the devil, so overfit the model. So what if you do random things? Now that you can edit, what do you do? And so what has some safety in place. So where as a user is changing the model, we show them the before after. So if you say, oh, I want to lift it. So you see on the right-hand side, accuracy, bounded accuracy, so all these metrics, how it's going to change. And not only that, we also keep the history. So if you change something, we're going to record everything, so operation that you have done. So those are some guardrail in place. And you might say, wow, that seems pretty ad hoc. Like, why would you ever let people change it? So apparently, fixing undesirable behavior is important. There are regulatory compliance. Now, for example, that you need to enforce monotonicity, for example, required by law. And also in practice, if you think about, say, wait, machine learning, it is coming up with some rules. So why does it make sense that you only rely on the training to determine what those rules are, while you know there are definitely some rules that doesn't make sense? Right? So for that reason, model editing is actually not something really surprising. So in practice, a lot of needs for it. Certainly, it's some ongoing work for doing it. So, for example, editing. So far we are doing manual editing, but you can imagine doing automatic editing, like helping the user to do it instead of like manually doing everything. Also coming up with guidelines, because when you have people interact with these machine learning models, to interact with them, to edit them, what are some best practices? Particularly, these are things that get called out actually about executive order. Like when you implement these, how do we do that? Also, a lot of times people work together. So how do we support collaborative editing, not only one person? Because often you need to involve domain experts. How do you have them all done together? So today I show you quite a lot. I whirlwind towards a lot of the examples in the three thrusts: Safe AI, Interpretable AI, and Trustworthy AI. And also connect them, really to motivate enough that so why we want to study all three, actually even more, but at least for these three, how do we study all together? Why was the significant for it? And with that, I'd like to thank you all for listening. Thanks. I believe I have time to the question if you might have any. Yes.
Questions? I know you have some questions.
Yes.
Hi, Polo. I do have a question. So how often are these mostly expert machine learner, people who are experts in machine learning, that you're making them more explainable, or do you see people using these in schools? Like, I mean, I know some at tech, but like at high schools or other places where they're using to try to explain machine learning?
Right, thanks for the question. So I'm asking, I think you're asking is that are these tools mainly built for experts? Would that also be for like high school students or maybe in different domains? Short answer is both. So I show you some of the tools like Summit, Neurocryptography, those are more for experts. But then the later collection of tools like, or show like CN Explainer, GangLab, Diffusion Explainer, those are actually for students. Actually, a lot of the majority of the user, the people visiting those tools, they are high school students. They are actually anyone that would use it. So I think we're particularly excited by that because initially, as I mentioned, we built this tool like mainly for ourselves. Like we want to learn about it, but then once we release it, it was like, wow, we really make it possible now that you eliminate all these barriers. Everyone who have a browser, like it could be on their phone even, now they can use it. So you no longer need to be expert Yeah.
Sorry. Give me some time to.
Okay, so I have a question
Yes.
about the GAN lab.
Yes.
And so, can you use this type of technology to then authenticate things that you find on the internet? Like, could we use this kind of in a backwards way to look at images and tell if they had been produced with AI or whether they were authentic?
Short answer would be work in progress. There's a lot of researchers, not in my group, but a lot of research has been working on it. It's closely tied to actually the latest like generative wave of generative AI, where they want to do we call data attribution, where they have a generative output, let's say Stable Diffusion or now DALL-E and others, where you have generative output. They want to know how it's generated, like what training data will lead to that, or maybe in the model itself, what's happening that lead to that. A lot of work on it. It's also closely tied to now executive order as well, like watermarking. So maybe during generative process, you may be able to insert some watermark that would be very, very hard for people to remove. Not perfect. There's some really latest result, like some published on ICML, for example, watermarking. There's some successes, but very quickly, often people say, oh, we can break it. So now it's kind of, cat and mouse right now. A lot of effort on it, but a lot of people want to accomplish that, yes. Sure, yes.
So for the watermarking, and you showed the different levels of analysis of an image.
Mm-hmm.
So can they do the watermarking on the different aspects of the image, so that it's on different levels, so that it's harder to remove? Is that kind of the stuff that's going on, or?
Great question. That's one approach. So people are still exploring different approaches because they want these, we call that kind of resilient watermarking that would not get destroyed or perturbed by the different transformation. So yeah, people are looking at it, the researchers, yes. Yeah, great question. Thank you.
Anything else?
Good.
Okay, well, we want to
Yes.
thank you very much.
Thank
for
you.
coming in today.
Thank you
That
for
was
having me.
amazing.
Thanks.